Okay, so thank you for coming. This lecture will be an analytic continuation of the previous talk. So the topic, unlike Will's lecture, is very classical. It deals with primes which are sums of two squares. And there's an old result of Fermat that says that an odd prime is a sum of two squares, like this, if and only if the prime is 1 modulo 4, so it's very easy to check this. Apparently this was written as a statement in a letter to Mersenne in Christmas Day, 370 years ago or something. And as far as I looked, Fermat didn't use to write out proofs. He just wrote statements that presumably he could prove. And some maybe he couldn't prove. It's not clear. A proof was eventually given by Euler, again, some time ago. Nowadays, this is very easy stuff. And I think next week I will teach it to my elementary number theory students. So people who haven't seen it are welcome to come. And among other things, it says that not only are primes which are 1 mod 4 a sum of two squares, but there's only one way to write them in this fashion, modulo changing the order of A and B and changing the signs of A and B. So in case you can write a prime as a sum of two squares, you can cook out a Gaussian integer out of it. So if P is A squared plus B squared, you can factor it as A plus IB times A minus IB. And these are Gaussian integers which are irreducible. In other words, they are primes. And my goal here is to understand how these Gaussian primes are distributed in the plane. So here is a picture of a few of these Gaussian primes in the complex plane. So this plot was produced by Bill Castleman for some popular article. I stole it from him, so I feel obliged to give him credit.
What is the resolution? It's 1 to how many?
So I don't know, because he didn't bother to write out. I'll show you some more pictures where I will write this out. But it's a pretty plot. Here's another plot, which I produced. So again, we write a prime as a sum of two squares. That gives us a point in the complex plane. The radius of this point is just the square root of the prime, and then there's an angle associated to it. And as I said, there's a unique representation if you require that A and B are positive and you pick which is bigger than the other. And that says that after you pick it the right way in the A-B plane, the angle, which is the arctangent of B of A, is between 0 and 45 degrees. So here is a plot of the angles for all primes between 1000 and 2000, which are 1 mod 4. There are 67 such primes, as it turns out. And here are the angles. And what I want to understand is the statistics of these angles. So do they behave like a random point set? Are there any patterns in these angles? And so on. So I'm not the first one to want to do this. So for instance, there is an old theorem of Hecke from about 90 years ago that says that as you vary over all primes which are 1 mod 4, these angles fill out densely this arc. And not only do they fill it out densely, they are uniformly distributed there, in the sense that if you look at the proportion of the angles which lie between alpha and beta, then in the limit, as you take more and more primes, you get the proportional length of that small arc. So this is uniform distribution of the angles. So I want to understand, once we know that there are no obvious patterns in there, that the angles fill out densely and uniformly this segment, and by symmetry all the segments on the unit circle, I want to ask what are the statistics, and I want to compare them to random uniform points. So I just take capital N angles, let's say the 67 primes between 1000 and 2000, which are 1 mod 4, and compare it to 67 uniform independent random points in this segment. So here's another picture where there's here there's roughly 180 such angles of primes from 1 to 2500, if I'm not mistaken. And this was stolen from some other place, which I forget right now. So I look at the primes from 1 to 2500. That gives me 180 angles.
So you use primes for ordering these angles?
No, I don't order the angles. I order the primes. The angles I don't know how to order. I don't want to do that.
So you mean first n
Prime.
So you mean that you take first n primes?
Yes, that's right. That's right. The angles are not ordered. Yeah. Okay, so the first thing, there's some trivial things one should notice, that it's not completely random. Of course it's not completely random because it's a deterministic thing, but also you can see it statistically if you look at the right microscope. So on the very smallest scale you can imagine, which is the scale of the average gap between these angles, the average gap here is 1 over n, where n is the number of angles. Then on the smaller scale, this is not random. So for instance, I can compare the following statistic. I take n random points and ask for the minimal distance between them. I take n random points in the interval 0, 1 or 0 pi over 4 and ask what is the minimal distance between two such points. The average distance is 1 over n. What's the minimal distance? The answer is almost surely the minimal gap between n random points in 0, 1 is 1 over n squared. That's it's called the birthday paradox. It's a computation that you can do quite easily. And here it turns out to be the minimal gap between these Gaussian angles is much, much bigger. It's of order 1 over n contaminated by a log. So it's not much smaller than the average gap. This is elementary. The next slide I'll show something even simpler. So from that point of view, these angles are not completely random. Here is a related statistic. Instead of the minimal gap, let's look at the maximal gap. Again, on average, it's 1 over n. You want to compare it to what happens if you look at the maximal gap between points, n random points in the unit interval. For n random points in the unit interval, yes. Thank you. Yeah, the maximum nearest neighbor gap. And then for n random points, the maximal gap is not much larger than the average gap. The average gap is 1 over n. The maximal gap is only bigger than that by a factor of log n. This is an old theorem of Paul Lévy from the beginning of the 20th century. Now here, the maximal gap is at least 1 over n to the half, so much, much bigger. And here's the argument. Took me longer to describe the result than to prove it. So you write the prime as the sum of two squares. So let's look at primes up to x. The number of such primes is roughly x over 2 log x. So since I'm worried about the exponent, x and n will be roughly the same here. And then if you look for, let's look, we'll find a big gap, a big hole near 0. So I just look, I'm trying to find points near 0. So the angle is going to be very small. And if the angle is very small, the angle and the tangent of the angle are the same. The tangent of the angle is the ratio of two integers. The nice thing about integers is that if they are not 0 and positive, then they are at least 1. This is one of the main tools for people in analytic number theory, which Igor was building up the subject. I'm trying to bring it down. This is, what did you call it? Stone axe. This is this is a piece stick, right? So let's use the stick. So the tangent is at least 1 over a, where a would be the bigger of the two. And a is at least square root of a squared plus b squared, which is p. So you get at least 1 over root p, and p is at most x. You get at least 1 over root x. X is roughly n times log n, where n is the number of angles of primes up to x. So you get that the maximal gap is at least 1 over square root n log n, because I found a big hole. So it's not random from this point of view.
Is this the only big hole?
So around any rational line, there is a big hole. The size is slightly smaller, depends on the height of the line. Same argument. And this is something that's well known to anyone who's thought about this. I don't know who to attribute it. And then I looked at instead of the maximal gap or the minimal gap, I looked at the typical gap. So here is a histogram of the nearest neighbor gaps measured on the scale of the mean space of the average gaps on the scale of 1 over n. And here is what happens if you just look at the distribution of nearest neighbor gaps for random points. This is an empirical plot. There's a solid line. The solid line is the exponential curve. So for n random points, almost surely, as n goes to infinity, the nearest neighbor histogram looks like this solid curve. And here is the picture for about 40,000 angles for all primes up to 1 million. My experience is that these are not exactly the same. But this is empirical data. I don't have a conjecture right now. It's up to you to formulate one.
The solid line is the same?
Yeah, the solid line is e to the minus s, which is the theoretical answer for the Poisson case, the random spacings. Okay, so I have nothing further to say about this, so let's move on and look at something which is slightly easier. So instead of looking at the smallest possible scale, namely the scale of the average gap, I want to look at slightly bigger scales. So instead of looking at intervals of size 1 over n, I want to look at bigger intervals, but which are still shrinking. So I remind you that Hecke showed that the angles of Gaussian primes are uniformly distributed. That is, if you take any fixed segment between 0 and pi over 4, the proportion of angles which fall in that segment is the proportional length of the segment. And the question is, does this remain true if you look at shrinking segments? Is the proportion of angles which fall in short segments still the proportional length of the segment? Oh, an even simpler question is does every short arc contain one of these angles? So I look at the first million primes, I get roughly 40,000 angles. Does every short arc contain them? Now, of course, the answer is not. If you take a very, very short arc, let's say shorter than 1 over 40,000, then typically it won't contain an angle. There's not enough angles to go around. So the question only makes sense if the arc is bigger than 1 over the number of primes that you're looking at. Okay, so that anything else, you're just wasting your time. You're doing statistics for the zero function. And once you have slightly bigger arcs, you can ask, A, do they contain an angle? And B, if that's true, are the angles uniformly distributed in such short arcs? Now, so again, this is known that if you assume the Riemann hypothesis, then you can take arcs as short as 1 over square root of the number of primes, roughly.
This is about existence of points or also about distribution?
It's also about uniform distribution. So not only do points exist, but within arcs which are not too short means 1 over square root of the number of primes, you have uniform distribution. And in particular, you have angles in there. Without the Riemann hypothesis, you have to replace a half by some smaller number. This was initiated by Kubilius in the 50s, and in somewhere in the Baltics, I think. Where is Kubilius? Latvia? Vilnius. And he had a school of people, and I think the world record is still held by one of that school from about 40 years ago, with some vulgar exponent which is less than a half but bigger than 0. The remarkable thing is you can get an exponent, and that's something, there's an analogous statement known in the theory of primes going from the 30s when you try to count primes in short intervals. So instead of the Riemann hypothesis, you use substitutes which are provable, called zero density theorems. Now, the remarkable thing here is that the Riemann hypothesis actually gives you the best result, because we saw that there's a big hole, that arcs which are bigger than 1 over square root of the number of primes, there are arcs which don't contain any prime angles. So, and this is one of these strange cases where the Riemann hypothesis gives you the truth. So I want to discuss what happens if you go below the range where the Riemann hypothesis helps you. So not only do I not know the Riemann hypothesis, I'm now going to venture further afield. We can't even count on the Riemann hypothesis to help me. So there's something you can do. You just say, okay, there is a big hole near 0, but that's not typical. Let's ask, what does a typical arc look like? So does a typical short arc contain a prime angle? Again, the arc had better be longer than 1 over the number of primes, otherwise I don't have a chance that it has any angles. And then the answer is that, still assuming the Riemann hypothesis, almost every arc which is as short, essentially as short as you can imagine, will contain an angle. So I'm writing this as a theorem with question marks because it wouldn't shock me if this is already known. I haven't found it in the literature, but I know how to do it, and people who know some analytic number theory would also know how to do it if I tell them that this is a correct statement. So it may well be in the literature. Now, how do you prove something about almost all short arcs? One way to do it, it's not the only way, is to compute the variance. And if you compute, so your statistic will be the number of angles lying in a random arc. You will compute the average, which is some trivial thing, and then give a bound on the variance. And once if we have a good enough bound on the variance, we will have a result for typical arcs. That's the thing to do. Okay, so I'll divide the relevant interval into k arcs of equal size and ask how many of the first n prime angles fall into each such arcs. So n is the number of primes up to x which are 1 mod 4, which is roughly half x over log x. And then, so I define this random variable. I look at an arc around theta of relative length 1 over k and ask how many of these prime angles fall into that, where I ask for the first n primes. By definition, the expected value is the number of primes divided by the number of arcs. It's a tautology. I'm not saying anything exciting here. So this is capital N, number of primes, divided by the number of arcs, the number of bins. Now the theorem is that under, still assuming the Riemann hypothesis, I can give a bound for the variance, which is n over k times some logarithmic factor. So n over k would be the variance for random points, and here it's slightly bigger by a logarithmic factor. And once you trace through you use Chebyshev's inequality, you will deduce that almost all arcs of length 1 over k contain one of these prime angles. So the main thing is to get a good bound on the variance, and I have to assume the Riemann hypothesis for here. I didn't see that the zero density theorems available are powerful enough to help me here.
I understand this gives you almost all arcs, but the question is, does the Riemann hypothesis or other methods allow you to get lower bounds on the variance to show that this is tight?
No, this is just an upper bound. I will discuss this in the next slide. Okay. And it's a theorem again with quotation marks because I do something a little bit different. I smooth it out, but I don't think this is. There are no analysts in the audience, so I will gloss over this point. Yes, Shahat, you're not considered an analyst by my standard. Okay, now to go to Ophir's question. That was an upper bound. We have a conjecture for the actual asymptotic of the variance. So the variance is useful. So something you start studying it for its own sake. And here's the conjecture. So again, you compare it with what happens for n random points divided into k bins. So here's an exercise. You take n random points in the unit interval, divide them into k bins. Expected number is n over k. The variance turns out to also be n over k. And here the conjecture is that the variance of these Gaussian angles is the random variance multiplied by either 1 or something, the ratio of the log of the number of bins to the log of the number of points. Okay, so here is the plot. The whole point of this lecture is to show this lousy plot. So the red line, so here I'm plotting the variance as a function of the ratio of log of the number of bins to the log of the number of points. And let's say I took all primes between 10 to the 9th or 8th and twice 10 to the 8th, which are 1 mod 4. I get 35,000 angles roughly. And then I change the number of bins. And for each such number of bins, I get a different variance. And after I divide by the random variance, I get something which is this blue scatter plot. It's actually terrible. So the analogous experiment for random points would give me this horizontal line, which is the ratio here would be 1. And here I get a slope which is something which has slope of 2 initially, and then it flattens out. And that's the conjecture. So the blue line is the conjecture, the red line is the random, and the scatter plot is the empirical data. It's continuous. This function is continuous. It's not smooth. It's piecewise continuous. It starts at, it's like 2x and then 1. It's a very simple function in the correct variables. So this is the conjecture. Now, where am I getting this conjecture? Source number 3 would be to actually do this experiment which I'm displaying. I don't know how convincing you find this plot. This is a really lousy plot. But I do see some rise and then some saturation at 1. It's pretty terrible plot. One reason could have been that I'm only taking 40,000 angles. We took more. It's still lousy. There's a reason. We believe we know the reason. We believe there's a correction, a logarithmic correction to this conjecture. After you divide by n over k, it should be either this plus something divided by log n. And here log n isn't such a small thing, so you don't see this happening in the limit. So eventually we will hopefully put this secondary term in, and then hopefully we'll get a better fit to this data. So that was motivation number 3. There are 2 other motivations. One is that I express this variance in terms of zeros of a certain family of L function, and then pretend that the zeros are zeros of a suitable ensemble of random matrices, and then compute the corresponding quantity. And I get, with the right dictionary, I get this match. I get this conjecture. I won't do this here. I want to go back to Will's lecture. Was kind enough to prepare the background for me and explain how you might get this conjecture, or at least half of it, using a function field analog. Okay? So we now go back to the world of polynomials over a finite field. So they are like the integers, and instead of primes, I look at irreducible polynomials, which are monic to play the role of positive polynomials. And then we have qualitative analogues. I can count prime polynomials rather than prime numbers. There's an analog of the prime number theorem. And instead of counting sums of 2 squares, I will look at polynomials which are norms from a certain quadratic extension of the rational function field. And the simplest one I could think of is adjoining square root of minus t. So I want prime polynomials which are a sum of a square of another polynomial plus t times the square of a polynomial. I like this simple model because it's got very simple features, but captures, I think, some of what I'm trying to model. Now, the advantage of working with polynomials over a finite field is that you can perturb, you can vary the size of a finite field, of the field of constants, and take it to infinity, which is what Will was doing in his lecture. While for the integers, God gave us the integers, you can't perturb them. I think Dedekind said that. So it's easy to tell if a prime polynomial is a sum of 2 squares in this sense. You just have to check if the quadratic sign of the constant term. Now I want to discuss the analog of the angle of such a prime. Now I can't plot these points in the plane, but I can look at the ratio of A over B. And that I'll call the slope. And this is, I'll just think of it as a Laurent series in 1 over t. So for instance, let's take this, when working over the field of 3 elements, like take this cubic polynomial, which happens to be irreducible, hopefully. And it is expressible as a square plus t times another square, in this way. And then the slope will be the ratio of t plus 2 to t plus 1, which is roughly 1 plus 1 over t, and so on. So you expand it in the formal Laurent series. That's easy to do. So that will be the slope. And the question will be to see how these slopes vary in this compact space. That'll be the analog of the unit interval as I vary these Gaussian primes, Gaussian prime polynomials. Okay, so given a slope, we define a sector around that possible slope by taking a rational function, that a over b, and expanding it in a Laurent series, as I did before, and just asking that the first three coefficients match the coefficients of the given slope. And that's how I'll divide the possible slopes into bins. The number of bins is the number of coefficients I have if I just specify the first kappa coefficients. So there will be q to the kappa such bins. So that's my capital kappa.
So you're saying it's compact because you can assume that there are no positive powers?
Yes, so again, let me go back. I'm assuming that the degree of the prime is odd, and that forces b to have the bigger of the degrees, and that means a over b has positive degree in 1 over t, non-negative degree. Just a choice, otherwise you flip it. Okay, so I divide the set of possible slopes into k bins, depending on the first kappa, the first three coefficients of the actual slope in the Laurent expansion, and ask how many of the of the capital N prime polynomials, which are sums of two squares in this form and of given degree, have slopes which fall in a given sector, like this. And that's this function n of lambda, which is this. Again, it's morally the same as Gaussian primes which have angle lying in a given arc. But it's not angle anymore, it's just the tangent of the angle. So it's morally the same thing. So I think. Then the first thing you check is that you do have equidistribution. Each sector will contain roughly the same number of slopes as long as the number of primes you're dealing with is bigger than the square of the number of bins. So it's the analog of what we had, assuming the Riemann hypothesis.
But here you use the Riemann
And
hypothesis for the function field?
yes, so that's why I didn't state any hypothesis here. It's a theorem.
No, but you use
I use, of
the
course, I
function
use
for the-
the Riemann hypothesis. I didn't say for which shell functions. That will come later. Okay. So again, the number of possible primes of given degree is the analog of x over log x. We know the prime polynomial theorem. And if you try to look at smaller sectors, meaning specifying more coefficients, then there will be the analog of big holes in here too. So you can't hope for an individual statement for any small sector. Okay. And now let's play the game of computing the variance. So for each sector, so you divide this possible slope into k bins and average over the bins and compute the variance of the number of slopes which lie in a given bin. And here we play this game in the limit of q going to infinity. And the answer is that we match our conjecture once you have a suitable dictionary set up. Unfortunately, so what we match is this part. So even though the empirical data looks very lousy here for over the integers, in the function field case we have a theorem which justifies this slope. And unfortunately, this regime we don't know. So this conjecture is now supported by an actual theorem for the variance in this regime. So where the slope is supposed to happen. Okay, so what's the tool? I have a few minutes, so I will dive into Will's lecture. So the way we pick out slopes is use a certain class of Dirichlet characters mod t to the correct power. I think in his lecture we'll call it this power d plus 1. I'll call it 2 kappa. We're looking at Dirichlet characters modulo t to the 2 kappa, which are even in the sense that they are trivial on the scalars, as in Will's lecture. And in addition, we call them super even if it's trivial not only on the scalars, but on all even polynomials. This is what the theory gives you. I don't have a good explanation of why it comes out. I still don't understand it. And you can count how many such super even characters there are, and the answer is q to the kappa, and q to the kappa is exactly the number of bins which I'm using. So it's not, so they are candidates for picking out which bin I lie in, which sector. And then the key fact is that I can tell if a polynomial has slope. So two polynomials have the same slope if and only if all super even characters agree on the suitable transform of these polynomials. This is a computation that Ezra came up with and which I still don't understand at the philosophical level. It's my problem, not your problem. The fact that you can prove something doesn't mean you understand it. It just means that you have something you can try to understand. Okay, so once you have this key fact, which sort of telling you that the slope has to do with an arithmetic progression modulo t to the 2 kappa in this particular regime, you do what Will did. You associated to each super even character an L function, normalized correctly, unlike in his lecture, so that the non-trivial zeros lie on the line real part of s equals a half. I don't know what you were doing in the. I blame jet lag for it. And once you do it properly, that L function, with or without trivial zeros, that's not the relevant thing, looks like a characteristic polynomial of a unitary matrix shifted. And that statement is called the Riemann hypothesis for curves over a finite field. That was proved by Andre Weil, and more or less proved by Andre Weil in the 40s. Okay. And then why is this useful for us? What we do is we show that the variance of the number of slopes in a sector looks like the average over all super even characters of the absolute value squared of the trace of a power of this Frobenius matrix. So if I know the statistics of the zeros of these L functions, I know the variance. So again, the details don't really matter right now. And then, okay, it leaves me with okay, step number 1 is you can use this to actually give a bound, because this is a unitary matrix. The trace is going to be independent of Q. So that gives you an upper bound on the variance, which is not terrible. So that's, I think, explains why you expect GRH to help you with giving upper bounds on the variance. But I want more. I don't want an upper bound. I want an asymptotic. That means I'd better be able to compute asymptotically the average of these powers of traces. And then what we do here is we ask Nick Katz, can you do this? And a day later he says, yes, I can. And the answer, so the way we compute this average is he shows that these classes, Frobenius classes, the zeros of these L functions, become uniformly distributed in the unitary symplectic group in the limit of Q going to infinity, assuming the size of the symplectic group is like at least 8 or something, I forget. I forgot to write down what their constraint is, but in the case which interests us. So that means you replace the average over all super even characters by the average over all unitary symplectic matrices. And then you just compute this or look it up somewhere, that this average is just the size of the relevant matrix. And then you input it into this formula and you find an asymptotic formula for the variance in terms of the parameters kappa and n, and then you interpret them in terms of the number of bins and number of points, and you get this function, which is exactly what we conjecture it to be. Not accidentally, because I first did this computation and then thought I'd better do a heuristic over the integers, and I had another way of doing that computation without being able to prove something there, and got the same thing. So in this regime, let's go back to Gaussian integers, Gaussian prime integers. In this regime, I have a theorem for the blue line in the function field case. In this regime, so this here, it means I don't take too many bins. The number of bins is less than the square root of the number of angles. This flat part is when the number of bins is bigger than square root of the number of angles. You still don't want to take more bins than angles, otherwise typically it'll get 0. And it turns out that the variance will still continue like that here, but it's not an interesting statement. So in this regime, I don't have a theorem in the function field case, even though the problem is well defined there. And that has to do with, I think, the wrong interpretation in terms of characters. So I am hoping to upgrade it at some point. And one reason why you get this kind of slope has to, if you play the same game with elliptic curves like Will did, you will get this slope. It's special to GL2. If you look at some GLN, then that slope will start here and then saturate. Okay, thank you.